Hello, welcome to today's lecture on deep learning. A lot of the progress that we have observed in computer vision and language modeling has been due to our ability to train deeper and deeper neural networks. Now, when we're training deep neural networks, several problems occur and, several methods have been developed to overcome these problems. And batch normalization, the topic of today's lecture, is one of these. So what are these challenges? One particular challenge is the issue that if we look at the representations that we create from the activations after each neural network layer, these values in these representations can have vastly different magnitudes. Now, for input data, a commonly used practice is just to standardize these input features. For example, to take each feature and set it to zero mean and unit variance by subtracting the mean of our training data and then dividing by the standard deviation of that feature. Now, batch normalization does a similar method for the hidden layers of a neural network. It is a problem that the activations that are generated between layers can vary by orders of magnitude. And obviously, if you look at, say, 100x differences between two layers, you might want to do something about it. For example, adjusting the learning rate. Now, that is not practical. And batch normalization was introduced by Joffe and Szigeti to avoid this drift in distribution by modifying the values of the activations and thus improve training of neural networks. So here you see the formula of the batch normalization operation. So if you have such a batch normalization layer, what you do is you take the input of that layer x, you subtract mu, the mean of this input, and you divide by sigma hat the standard deviation of this x. On this, you pointwise multiply by some parameter gamma, and you add a constant beta to it. And as we said, this mu hat is the estimate of the mean. And sigma hat is the estimate of the standard deviation, so the square root of the variance. How do we estimate this? Well, by using a single mini batch. So for one mini batch, we compute mu, so the average over the values of this mini batch, and sigma hat, 1 divided by n minus 1 times the sum of squares of the values minus their estimate of mu. And the result is that the activations are approximately rescaled to 0 in the mean and unit variance. Why approximately? Well, because we have these two parameters here, gamma and beta. And these are a coordinate-wise scaling coefficient and an offset. So these scaling coefficient gamma and this offset beta are effectively regularizers of this batch norm layer in case something goes wrong with our estimate sigma hat and mu hat. One result of using this batch norm is that the activations of these intermediate layers cannot diverge much longer from each other. So between two different layers, the magnitude of these weights will always be of a similar magnitude because they are basically forced to have a variance that is close to 1 because we divide by our estimate of sigma hat. So we always rescale them after each layer. By avoiding to have, these huge differences between different layers, we avoid the case where at some point you have a close to zero activation, then you have a giant activation and corresponding also values of the gradients, which means that we can be more aggressive in picking large learning rates. So our training will be more robust to different choices of the learning rate, which means that we can pick larger values in order to make more progress over time. Now, there are some cases where the activations may actually need to differ from standardized data, and that is why we introduce these additional parameters gamma and beta. Now, where do these estimates of mu and sigma come from? In principle, we could use all our training data. Now, as you could already infer from the name, batch norm makes use of an estimate that comes only from our mini batch. So we're using only our mini batch, say 128 samples or 64 samples, to estimate their mean and the standard deviation, which means that we will get different estimates for each mini batch. So we have a noisy estimate of mu and sigma. Here you see the formulas of the estimates. So we're basically computing the average over our mini batch. So 1 divided by the size of the batch times the sum of the x values of the batch, so the average. And then we set sigma square, the variance, to the estimate of the sample variance, 1 divided by the size of the mini batch times the sum of squares of the difference between the value x and our estimate mu hat b plus an epsilon. And this epsilon takes care of the case where this, for example, might be 0 because our mini batch might be constant or so. The problem, if we had an estimate that would be 0, is that we would be dividing by 0. So we want to avoid dividing by 0. So we will always want to have a value that is larger than 0. Thus, we add a small constant epsilon that is positive. Now, the fact that we have different estimates of mu and sigma for each mini batch might seem like a downside, but in practice it actually tends to act as a regularizer that is actually quite useful. And there is some work by various authors that relate these properties of batch normalization to A, Bayesian priors, and B, various penalties. Depending on the neural network architecture that we're using, we might have to modify batch norm slightly. For example, if we use a fully connected neural network, then we would typically apply batch norm between the affine transformation and the activation function. So if x equals wu plus b, where x is the input to batch norm, this is the affine transformation, then we would actually apply batch norm in here. So it's sort of in the middle of the fully connected layer that we're introducing this additional layer. In convolutional layers, we typically don't want to apply batch norm for each pixel separately, but rather we would apply it to all the pixels at the same time. Say we have a convolutional layer that generates a representation of size p times q, where p is the height of the transformed representation and q is the width of this representation, and m is the batch size. Then we would carry out batch normalization on a tensor of size m times p times q, where batch size times height times width. Then we would take this tensor and compute a single mean and a single standard deviation for this tensor and apply batch norm to the values of this tensor by subtracting the mean and dividing by the standard deviation. Now, of course, convolution typically has multiple output channels, and if you see here, these dimensions do not contain the number of channels. That is because we would typically apply batch norm for each channel separately. So if we have additionally a number of channels, that would be an additional dimension of this output tensor. We would still look at only the subtensor that correspond to a single channel at a time, apply batch normalization on this channel, then estimate a new mean and a new standard deviation for the next channel and apply batch norm and so on and so forth. There's also a difference between applying batch normalization at training time, where we have mini batches, and at test time, where typically we are looking at a single example at a time and we want to make a prediction, which means we cannot really estimate means and variances for this example. Thus, typically we would have to fix a value of mu and sigma, for example, by looking at a moving average or by just picking a single fixed value, say from the training data. Thus, remember, batch normalization behaves differently between training time and test time. So let's summarize batch normalization. Well, during training, batch norm adjusts the layer activations of the neural network continuously to avoid differences between the magnitude of the activation between different layers, but also of the same layer over time, because as you make an update to your parameters, also the resulting activations even for the same batch or for the same example would differ. Thus also the magnitude can go up or down over time. And batch norm basically keeps the variance and the mean of these activations constant between layers and over time. The implementations of batch norm for fully connected layers and for convolutional layers are slightly different. So for convolutional layer, we would look at a single output channel at a time, but look at the whole height and width of our output representation over this batch. And similar to what we have seen for dropout, we have a difference between applying batch norm during training and during testing, because at testing we don't typically have access to a whole batch, but rather we would use a fixed value of mu and sigma to apply batch norm. And during training, batch norm, because it changes over time and because there is the variance of the small batch in the mu and the sigma, it actually does have a regularizing effect on the neural network. It also allows us to pick larger learning rates. And of course, if you look at the estimates of mu and sigma, the whole batch norm layer, of course, is differentiable, so we can actually apply it in a neural network. So with this summary, I want to say goodbye and see you next time. Bye-bye.